Hello again. In this lecture, we're going to study the analysis procedure for frames and machines. So far we have studied trusses, and I'm sure you remember that trusses are triangular assemblies made of two-force members. So all members in a truss are two-force members. That means these members are pin-ended and they have no forces along them. That makes them two-force members. Now, for the frames and machines, these are assemblies of members which in general are not two-force members. In other words, their ends might not necessarily be pinned, or most commonly they have forces or moments acting along their length. That makes them not two-force members. Frames usually have non-moving parts. So for example, like a building structure with columns and beams, whereas machines have moving parts. They can be various, for example, mechanical devices. Now, although they are different from this point of view, from the point of view of equilibrium, both systems are analyzed using the same principle. So from the point of view of analysis, there is no difference between a frame or a machine. That's very important to remember. Now let's talk a little about the principles of analysis. Whenever you look at a question, you start a question dealing with a frame or a machine, the first thing you should do always is look for and identify any two-force members, if any, in the structure. Why? Because if you know the two-force members, you can actually reduce the number of unknowns by actually knowing the direction of the resultant force at the end of the two-force members. So, for example, if we deal with a straight member like the one in a truss, the reaction forces will line up with the line connecting the ends of the member. So in this case, it's the member itself. So we know the direction of the resultant force. In other words, we know these angles. So therefore, knowing one component would help us know the other component automatically. Two-force members can also be bent, such as this one, and again the same rule applies. That is, the reaction forces at the end of the two-force member line up with a line connecting the ends of the member. And, of course, the same rule will apply also if the two-force member is, for example, curved, like this one. And again, similar rule, the internal reaction forces at the ends of the member line up with the line connecting the ends of the member. So it's very important if you can identify the two-force members again, because you will reduce the number of unknowns and hence the number of equation, and therefore the solution will be much simpler. Now, once you have identified the two-force members, you would have to determine in a question whether the frame or the machine is rigid or non-rigid when it's removed from its supports. In other words, you have to imagine that you've removed the system from its supports, and by looking now at the system, you have to figure out whether the system can change shape easily, freely, or not without the external supports. And this may be a little challenging sometimes, but you'd have to somehow try to make this judgment. But you can also look at the type of the supports, and based on the type of the number of supports, you can decide whether the frame is rigid or non-rigid. For example, rigid systems, they will act as a rigid body overall, so they cannot change shape if removed from their supports. Like this one here in this picture. And in order for this system to achieve equilibrium, all you need for a rigid body is to have three external reaction forces that are neither parallel nor concurrent at a point. If that's the case, so you have only three external reaction forces for a given frame or a machine, then you can actually write your three equations of equilibrium for a rigid body overall, and you can solve for all these three external reaction forces. And that's good because you now know at least these forces externally to the body. It's a good start for solving the question. Now, for non-rigid systems, these, as I mentioned, are not rigid internally, so they can change shape once you remove them from their supports. Imagine, for example, scissors or pliers that you can change shape if they're not supported externally. In a simplified way, you can have a system like the one I'm drawing here. Two rigid systems pinned to each other, and in order to achieve equilibrium, there are two external pins like so. So now if you count the reaction forces, you can see that there are more than three external reaction forces that are necessary. And those reaction forces above the first three are necessary to compensate for the internal instability of the member. What do we do in this case? Well, we can solve for as many unknown reaction forces as we can. Sometimes we can solve for some, sometimes we cannot solve for any. In this case, in order to see what you can solve for, the clue is to look and see whether these reaction forces or the supports line up. So, for example, in this diagram that I drew, you can see that the supports at A and B actually do line up along a horizontal line that goes through A and B, like so. And therefore, if you, for example, sum the moments at B, then you can solve for AY because BX, BY, and AX intersect at B. And similarly, if you sum the moments at A, you can solve for BY because AX, AY, and BX would intersect all at A. So in this case, you can solve for two reaction forces, AY and BY. So your main goal at this point is to try to solve for as many external unknown forces as you can, because later on in the subsequent steps you will already have some known forces that you can use in your solution. Sometimes you cannot solve for any external forces, and that's a little unfortunate, but it is what it is. So then you would have to simply proceed to the next step without knowing any external forces. But if you can solve for some external forces, you should do so because your subsequent solution will be much simpler. Once we've done so, all we have to do now is split the frame or the machine into its individual components, and then we will have to analyze the individual components separately, sometimes sequentially or jumping from one component to another and then sometimes back to the first one and so forth. And in doing so, we will apply, when splitting the frame, we will apply the principle of action and reaction that you should pay attention to very carefully. For example, if in a frame or a machine there are two members that are pinned together at C, for example, at point C in this case, which is at the intersection of these two members, then if we have to split these members separately, so split the pin, then this would be the member A, and this one would be member, say, B. And then you'd have, in each of these free body diagrams, you'd have to replace the other member by internal reaction forces, like for example Cx and Cy, here both positive. Then using the principle of action-reaction on the other member, these reaction forces must be opposite, must have opposite signs. So in this case, Cx and Cy will be negative. So this is very, very important. And if you don't do so, it would be a major error in the solution of the question. So the direction of the reaction forces can be assumed, but that must be equal and opposite on the other member. So we assume the direction because we don't know whether they're positive or negative, but always they have to have opposite signs on the two members that were split. Now, the other important thing is, if you, after writing the equations of equilibrium, if one result is negative, you should not go back and change the sign of that force on the previous free body diagram, because now if you do so, your equations will be wrong. Instead, what you should do, you should carry on with a negative sign that you have obtained. So you have to remember that that force was negative. And let's look at a fictitious example just for the sake of understanding this principle. Assuming that these two members were connected at C and now are split, and on the left hand free body diagram we have the reactions in red Cx and Cy, like so, and of course some other forces acting along the member. And then on the right hand side free body diagram, on the other member, Cx and Cy look like so, with opposite directions from the other side. And of course on this member there will be some other forces acting at other points along the member. So this would be, say, free body diagram 1, the free body diagram 2, and let's say that we've written an equation of equilibrium on the first free body diagram, and from this equation of equilibrium the vertical reaction force at C resulted negative. So therefore the reaction force on the free body diagram will have the opposite sign. Then on the second free body diagram, if you write the same equation of equilibrium, then you should carry the sign. So Cy points downwards, and then carry the negative sign in the bracket like so. So downwards, a negative force. That's the first minus standing for, and then the second minus in the bracket stands for the actual sign of the force obtained from the first equation. Now, at the end of the solution though, you have to draw new free body diagrams of the members that were split, and on these free body diagrams you would have to draw the forces with the correct directions and correct magnitudes. And this will represent your final answer. You'll always have to end a question like that, with free body diagrams of the members. So thank you very much for watching this lecture, and we will do some examples with frames and machines in the next ones.